Example 2, we want to consider the parabola y is equals to x squared plus 5x minus 6. And we want to find the derivative of the parabola by first principles. So in this case, right, we've got dy dx. So we're looking for the derivative, okay, well, in other words, the gradient function. And we know that dy dx is equals to limit as h approaches 0 of function x plus h minus function x all over h. So in this case, the function is going to be given by just x squared plus 5x minus 6. So function x plus h is therefore equals to x plus h squared plus 5 times x plus h minus 6. If I just take a moment to expand this, this is going to be x squared plus 2xh plus h squared plus 5x plus 5h minus 6. So if I put my function x plus h and function x back into my first principle here, we're going to get limit as h approaches 0. Function x plus h is x squared plus 2xh plus h squared plus 5x plus 5h minus 6. I'm keeping the bracket around here literally just for aesthetics. Minus function x, which is just going to be x squared plus 5x minus 6. Now the bracket here is functional because take note that we have a minus sign out of the front, and this is all over h. So if we do a little bit of simplification first, right, if I compare across the two brackets, I can see that I've got an x squared minus an x squared. We've got a 5x minus a 5x, and we've got a minus 6 minus minus 6. So these cancels off, and what I'm essentially left with is limit as h approaches 0 of 2xh plus h squared plus 5h, and this is all over h. And what is important here is that the expression in the top, the three terms, they all contain a factor of h. So therefore I can factorize that out, giving us limit as h approaches 0 of h brackets 2x plus h plus 5, and this is divided by h. Okay, so we can cancel the h out from the top and the h out from the bottom, and that's going to leave us with limit as h approaches 0 of 2x plus h plus 5. So now if I make the substitution for h is equal to 0, this term here disappears, and we're left with just simply 2x plus 5. So 2x plus 5 is therefore the derivative or the gradient function to the parabola y is equals to x squared plus 5x minus 6, right? And of course, the gradient function is a function because for a parabola, we know that the gradient changes for different values of x. So that's why we have a function as the derivative. So before I move on, just one note here that when we're doing first principles, the limit as h approaches 0 stays at the beginning of the expression for every single line until we make the substitution for h is equal to 0. And after we make the substitution for h is equal to 0, then the limit operator disappears, right? Until we have done that process, it stays there. Okay, so make sure you guys keep that in mind. Now for part 2, we want to hence find the gradient of the tangents at the point where the parabola intersects with the x-axis. So we've got the parabola given by y is equals to x squared plus 5x minus 6, and we know that the derivative dy dx is given by 2x plus 5. So I'm just going to digress a little here. Okay, I'm going to bring out a graph. So for the parabola x squared plus 5x minus 6, we know that this factorizes into x plus 6 times x minus 1. So here, if I actually sketch it, I have the x-axis, I have the y-axis. So this is y, this is x, this is the origin, and we know that this parabola, roughly speaking, is just going to look a little bit like this, and we know that it's got an x-intercept at -6, and we also know that it's got an x-intercept at 1. Okay, I have a tangent over here, and then at x equals to 1, I have a tangent over here. Okay, and because obviously I didn't draw my parabola very well, okay, the tangents are not very accurate. Okay, if the graph was done perfectly, these two tangents are actually going to be symmetrical. Okay, as in they will look symmetrical in the sense that one is downward sloping and the other one's going to be upward sloping with exactly the same gradient. Now, how do I actually show this algebraically? So now we've got the derivative, right? The derivative is the gradient function. And for this parabola, at this particular point when x equals to -6, if I want to find the gradient of the tangent or the gradient of the curve at this point, I simply take x equals to -6 and I'm going to substitute it into the derivative. So here, at x equals to -6, dy dx is going to turn out to be 2 times -6 plus 5. That's -12 plus 5, which is equals to -7. And this represents the gradient of tangent at x equals to -6. For the other x-intercept at 1, so at x equals to 1, dy dx is equals to 2 times 1 plus 5. So that's going to be 2 plus 5, which is equals to 7. So the gradient of the tangent at x equals to 1 is therefore 7. And we should be able to see algebraically speaking here that the gradients are exactly the same, but one is negative while the other is positive, and that's essentially to do with the symmetry of the parabola. Okay, so that being said, this is essentially the idea of how we use the derivative. Okay, the derivative is a gradient function. If we want to find the gradient at a specific point on a non-linear function, take that particular x value, substitute it into the derivative or the gradient function, and the value that comes out will represent the gradient of the tangent or the gradient of the curve at that particular point. So that being said, this concludes example 2.